Space represents one of the most profound mysteries confronting human understanding, challenging our fundamental concepts of existence, infinity, and reality itself. When we contemplate whether space ends, we venture into territory that pushes the boundaries of physics, mathematics, and philosophy. The question itself reveals the limitations of human intuition when applied to cosmic scales and forces us to grapple with concepts that defy everyday experience. Modern cosmology suggests that space as we understand it is not simply an empty container in which objects exist, but rather a dynamic, evolving entity intimately connected to time and matter. The fabric of space-time, as Einstein revealed, can be curved, stretched, and manipulated by the presence of mass and energy. This revolutionary understanding transformed our conception of space from a static backdrop to an active participant in the cosmic drama. The question of whether space ends cannot be answered without first understanding what space actually is and how it behaves on the largest scales imaginable. Current scientific evidence suggests that the observable universe extends approximately 46.5 billion light years in all directions from Earth, creating a spherical volume of space that contains everything we can potentially observe. However, this observable boundary does not necessarily represent the edge of space itself, but rather the limit of our ability to gather information about distant regions. The expansion of space itself, discovered by Edwin Hubble in the 1920s, adds another layer of complexity to our understanding, as it suggests that space is not only vast but continuously growing, carrying galaxies away from each other at ever-increasing rates. The concept of an infinite universe presents both mathematical elegance and philosophical challenges that have captivated thinkers for centuries. If space truly extends infinitely in all directions, then it contains infinite matter, infinite stars, infinite galaxies, and infinite possibilities. This infinity would mean that every possible arrangement of atoms that could exist does exist somewhere in the vast expanse, leading to the mind-bending conclusion that there are infinite copies of Earth, infinite versions of every person who has ever lived, and infinite variations on every possible scenario. The mathematical framework supporting infinite space relies on assumptions about the overall geometry and curvature of the universe, which current observations suggest is remarkably close to being perfectly flat. A flat universe, according to cosmological models, would indeed be infinite in extent, stretching endlessly in all directions without boundary or edge. However, the very concept of infinity troubles many philosophers and scientists, as it leads to paradoxes and contradictions that challenge our understanding of causality, probability, and meaning. If space is infinite, then the probability of any specific event becomes simultaneously zero and inevitable, creating logical puzzles that have no clear resolution. The infinite universe hypothesis also raises questions about whether truly infinite quantities can exist in physical reality, or whether they represent mathematical abstractions that approximate, but do not perfectly describe, the actual structure of spacetime. Alternative cosmological models propose that space, while vast, might indeed have boundaries or edges, existing within a finite volume that could theoretically be measured and described. These finite universe models suggest that space curves back on itself in ways that are difficult to visualize, but mathematically consistent, similar to how the surface of a sphere is finite, yet has no edge or boundary when traveled along. In such models, a traveler moving in one direction for an infinite amount of time would eventually return to their starting point, much like circumnavigating the Earth's surface. The geometry of a finite universe could take various forms, including spherical, toroidal, or more exotic topological shapes that satisfy the mathematical requirements of general relativity while providing closure to the spatial dimensions. These models offer the intellectual satisfaction of a universe with definite, measurable properties, while avoiding the philosophical complications of infinity. However, they raise their own questions about what might exist beyond the boundaries of such a finite space and whether the concept of beyond has any meaning in this context. Current observational evidence cannot definitively distinguish between finite and infinite universe models, as both make similar predictions about the properties of space within the observable region. The curvature of space appears to be extremely close to zero, which could support either a flat infinite universe or a very large finite universe, whose curvature is too slight to measure with current precision. The relationship between space and time, unified in Einstein's concept of spacetime, adds temporal dimensions to the question of spatial boundaries that complicate simple geometric interpretations. Spacetime represents a four-dimensional manifold where the three dimensions of space are inseparably linked with the dimension of time, creating a unified framework for describing physical reality. The expansion of the universe occurs not just in space, but in space-time itself, meaning that the very fabric of reality is stretching and evolving as cosmic time progresses. This expansion began with the Big Bang approximately 13.8 billion years ago, representing not just the emergence of matter and energy, but the beginning of space-time itself. Before this cosmic beginning, the concepts of space and time, as we understand them, did not exist, making questions about what came before, what lies outside, fundamentally meaningless within our current theoretical framework. The expansion of space-time continues today, accelerating under the influence of dark energy, a mysterious force that comprises roughly 68% of the universe's total energy density. This acceleration suggests that the rate of expansion is increasing, potentially leading to scenarios where distant galaxies become forever unreachable as space itself expands faster than light can travel between them. The ultimate fate of spacetime expansion remains uncertain, with possibilities ranging from eternal expansion and cosmic heat death to eventual contraction in a big crunch scenario, or more exotic outcomes involving the fundamental structure of spacetime itself. Quantum mechanics introduces additional complexity to our understanding of space by suggesting that even empty space is not truly empty, but filled with quantum fields that fluctuate at the smallest scales imaginable. These quantum fluctuations create virtual particles that briefly pop into existence before annihilating each other, giving rise to measurable effects such as the Casimir force and contributing to the vacuum energy density of space. The quantum vacuum represents a seething foam of activity at the Planck scale, where the smooth geometry of classical spacetime breaks down into a probabilistic landscape governed by the uncertainty principle. At these incredibly small scales, approximately 1035 meters, the very notion of distance and spatial separation becomes fuzzy and ill-defined, suggesting that space itself might have a granular or discrete structure rather than being perfectly continuous. This quantum graininess of space-time could have profound implications for understanding whether space can truly extend infinitely or whether the discrete nature of quantum geometry imposes natural limits on spatial extent. If dark energy represents a true cosmological constant, then space will continue expanding exponentially forever, potentially creating infinite volume, even if it began with finite extent. Alternatively, if dark energy is dynamic and can change over time, it might eventually weaken or reverse, leading to scenarios where the expansion of space halts or reverses, potentially imposing different types of boundaries or limits on spatial extent. So, the holographic principle, emerging from studies of black hole physics and string theory, suggests that all the information contained within a volume of space can be encoded on its boundary surface, implying fundamental limits on the information content and perhaps the very nature of spatial dimensions. This principle arose from attempts to understand the entropy and information content of black holes, which Stephen Hawking showed must have entropy proportional to their surface area rather than their volume, contrary to ordinary thermodynamic systems. The holographic principle generalizes this insight, proposing that the maximum information content of any region of space is determined by the area of its boundary rather than its volume. suggesting that three-dimensional space might be fundamentally emergent from information encoded on two-dimensional surfaces. This has profound implications for understanding whether space can extend infinitely, as infinite space would seem to require infinite information content, potentially violating the holographic bound. Some interpretations of the holographic principle suggest that space itself is not fundamental, but rather emerges from more basic information theoretic process, similar to how temperature emerges from the statistical behavior of molecular motion without being a fundamental property of individual atoms. In this view, questions about whether space ends might be asking about the wrong level of description, similar to asking whether temperature has boundaries when temperature itself is an emergent property of underlying microscopic processes. The holographic principle has found concrete realizations in certain theoretical models, particularly in the context of the ADCFT correspondence, where gravity in a higher dimensional space is equivalent to a quantum field theory on its lower dimensional boundary, providing mathematical frameworks for understanding how spatial dimensions might emerge from non-spatial information. Observational cosmology provides crucial evidence for understanding the large-scale structure and potential boundaries of space through measurements of the cosmic microwave background radiation, the distribution of galaxies, and the expansion history of the universe. The cosmic microwave background, CMB, represents the oldest light in the universe, emitted approximately 380,000 years after the Big Bang, when space first became transparent to photons. This radiation carries detailed information about the geometry, composition, and evolution of space on the largest observable scales, providing precision measurements of fundamental cosmological parameters. The nearly perfect uniformity of the CMB temperature across the sky, with tiny fluctuations at the level of parts per million, suggests that space has very little curvature on large scales, supporting models where space is either exactly flat and infinite or very nearly flat and extremely large. The pattern of temperature fluctuations in the CMB also provides information about the topology of space, potentially revealing whether space has exotic geometric properties or connections that could indicate finite extent. Searches for repeated patterns in the CMB that might result from light having traveled around a finite universe have yielded negative results, suggesting that if space is finite, it is larger than the observable universe and cannot be detected through current observational methods. Galaxy surveys mapping the three-dimensional distribution of matter across billions of light years provide complementary information about the geometry and evolution of space, revealing the cosmic web of filaments and voids that trace the underlying gravitational structure of spacetime. These observations consistently support cosmological models where space extends far beyond the observable horizon, but they cannot definitively determine whether this extension is finite or infinite. The mathematical frameworks used to describe space in modern physics, particularly the tools of differential geometry and topology, provide rigorous methods for analyzing questions about spatial boundaries and extent while revealing the deep connections between geometric properties and physical laws. Differential geometry allows physicists to describe curved spacetime using coordinate systems and metric tensors that specify how distances and angles are measured in different regions, providing the mathematical foundation for general relativity and cosmological models. The curvature of spacetime, described by the Riemann tensor and its contractions, determines how matter and energy move through space and how space itself evolves over time. Topological properties of space, such as its connectivity, orientability, and boundary conditions, provide additional constraints on possible spatial geometries that are independent of local curvature measurements. The classification of three-dimensional manifolds, a central problem in pure mathematics, directly relates to understanding the possible global structures that space could have, including finite models with no boundaries and infinite models with various types of asymptotic behavior. These mathematical tools reveal that the question, "Does space end?" has multiple possible answers depending on the specific geometric and topological properties of the universe, each corresponding to different mathematical models that could potentially describe physical reality. The interplay between mathematics and physics in cosmology demonstrates how abstract mathematical concepts can provide concrete insights into the nature of physical space, while observations and experiments can validate or constrain mathematical models of spatial geometry. Modern techniques in computational cosmology allow researchers to simulate the evolution of different universe models with various boundary conditions, testing how different assumptions about spatial extent affect the predicted properties of galaxies, cosmic microwave, background patterns, and other observable phenomena. Philosophical implications of infinite or finite space extend far beyond technical scientific questions, touching on fundamental issues of meaning, causality, and the nature of existence that have engaged human thought for millennia. The possibility of infinite space raises profound questions about the uniqueness and significance of any particular events or arrangements of matter, as infinite space would contain infinite repetitions of every possible configuration, including infinite copies of Earth, humanity, and every individual person. This leads to philosophical puzzles about personal identity, moral responsibility, and the meaning of choice in a universe where every possible decision is realized infinitely many times across infinite space. The anthropic principle, which attempts to explain certain properties of the universe by noting that they must be compatible with the existence of conscious observers, takes on different meanings in infinite versus finite space models, as infinite space would contain observers in every possible cosmic environment, while finite space might impose constraints on the types of complexity and consciousness that can emerge. The heat-death scenario, where the universe eventually reaches maximum entropy in uniform temperature, has different implications for finite versus infinite space. With finite space potentially reaching true equilibrium, while infinite space might maintain pockets of low entropy through statistical fluctuations for arbitrarily long times. Questions about the ultimate fate of information, consciousness, and meaning in the far future depend critically on whether space provides infinite room for continued evolution and complexity, or whether finite boundaries impose ultimate limits on growth and development. The intersection of physics and philosophy in contemplating spatial infinity demonstrates how scientific understanding can both inform and be informed by deeper questions about the nature of reality, purpose, and human existence within the cosmic context. The search for evidence of spatial boundaries or infinite extent drives cutting-edge research in observational cosmology, theoretical physics, and experimental techniques that push the limits of human technological capabilities. Future space-based telescopes and observatories will map the cosmic microwave background with unprecedented precision, potentially detecting subtle signatures of finite space topology or confirming the flatness of space to levels that strongly support infinite extent models. Advanced gravitational wave detectors might eventually detect signals from the earliest moments of cosmic history, providing new windows into the fundamental structure and extent of spacetime that complement electromagnetic observations. Particle accelerators probing ever higher energy scales could reveal new physics that affects our understanding of space at quantum levels, potentially discovering evidence for extra dimensions, discrete space-time structures, or other exotic properties that influence questions about spatial boundaries. Theoretical developments in quantum gravity, string theory, and cosmological modeling continue to refine our mathematical frameworks for understanding space, potentially leading to new predictions that can be tested through observation or experiment. The development of quantum computers and advanced computational techniques enables more sophisticated simulations of universe evolution under different assumptions about spatial geometry, helping to identify observable signatures that could distinguish between finite and infinite space models. International collaborations involving thousands of scientists and billions of dollars in research funding reflect the profound importance of understanding spatial extent for our comprehension of reality itself. The technological challenges of probing the largest scales of space and the smallest scales where quantum effects dominate require innovations in detector technology, data analysis techniques, and theoretical modeling that often find applications far beyond cosmology, driving advances in computing, materials science, and engineering. The relationship between local and global properties of space illustrates how the question of spatial boundaries connects intimate human experience with the grandest scales of cosmic structure, revealing deep principles about the nature of physical law and mathematical truth. Local measurements of spatial properties, such as the geometry around Earth or within the solar system, provide limited information about global spatial structure, similar to how walking around a small area of Earth's surface provides little direct evidence for the planet's spherical shape or finite area. The principle of general covariance in relativity ensures that local physics remains the same regardless of global spatial topology, meaning that inhabitants of finite or infinite universes would experience identical physical laws and phenomena in their immediate vicinity. This separation between local and global properties reflects deeper principles about the nature of physical theories, which typically specify local field equations and boundary conditions rather than global geometric constraints, allowing multiple possible global solutions that satisfy the same local physics. The process of extending local measurements to infer global properties requires sophisticated statistical analysis, theoretical modeling, and careful consideration of observational selection effects that could bias our understanding of spatial extent. Homogeneity and isotropy, the fundamental assumptions that space looks the same at all locations and in all directions on large scales, provide the theoretical foundation for using local observations to infer global properties. But these assumptions themselves must be tested and validated through careful observation. The cosmic principle, which assumes that humans occupy a typical location in space rather than a special or privileged position, guides the interpretation of astronomical observations and the extrapolation from local measurements to global conclusions about spatial structure. This interplay between local experience and global inference demonstrates how human understanding progresses from immediate sensory experience to increasingly abstract and comprehensive theories about the nature of reality. Current technological limitations constrain our ability to definitively answer questions about spatial extent, but rapid advances in observational capabilities and theoretical understanding suggest that significant progress may be possible within the coming decades. The observable universe represents a fundamental limit imposed by the finite speed of light and the finite age of the universe, creating a horizon beyond which information cannot reach us regardless of the true extent of space beyond. This observational horizon is not static, but grows over time as light from increasingly distant regions has time to reach Earth, potentially revealing new information about spatial structure and extent. However, the accelerating expansion of space driven by dark energy means that there will always remain regions of space that are forever unobservable, placing ultimate limits on our ability to map the complete spatial structure of the universe through direct observation. Advances in precision measurement techniques, including improved distance indicators, better statistical methods for analyzing cosmic microwave background data, and more sensitive gravitational wave detectors, continue to refine our understanding of cosmic geometry and expansion history. Theoretical developments in fundamental physics might reveal new connections between quantum mechanics and gravity that provide indirect evidence about spatial structure through laboratory experiments or particle accelerator studies. The possibility of detecting quantum entanglement or other quantum mechanical phenomena on cosmic scales could provide new tools for probing the global structure of space in ways that complement traditional astronomical observations. Machine learning and artificial intelligence techniques applied to astronomical data analysis enable the detection of subtle patterns and correlations that might reveal signatures of finite space topology or other exotic spatial properties. The integration of multiple observational probes, including electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, provides complementary information about spatial structure that can be combined to test different theoretical models of cosmic geometry and extent. The implications of answering the question, "Does space end?" extend far beyond academic curiosity, potentially affecting humanity's long-term future, our understanding of consciousness and meaning, and our approach to fundamental questions about existence and purpose. If space is infinite, humanity faces the prospect of unlimited expansion and growth, with infinite resources, infinite worlds, and infinite opportunities for development and exploration across cosmic time scales. Infinite space would ensure that no matter how far civilization advances or how much it grows, there would always be new frontiers to explore and new challenges to overcome, providing eternal purpose and meaning for conscious entities. Conversely, finite space would impose ultimate limits on growth and expansion, requiring humanity to develop sustainable practices and closed-loop systems that can operate within fixed spatial boundaries for indefinite periods. The heat-death scenario, where the universe reaches maximum entropy and uniform temperature, would have different implications in finite versus infinite space, affecting the ultimate fate of consciousness, information, and organized complexity. Understanding whether space ends could inform strategies for long-term human survival and development, influencing decisions about space exploration, resource utilization, and the development of technologies for interstellar and intergalactic travel. The psychological and philosophical impact of knowing whether space is finite or infinite could profoundly affect human culture, religion, and individual worldviews, similar to how the Copernican revolution changed humanity's understanding of its place in the cosmos. Educational systems and public understanding of science could be transformed by definitive answers to questions about spatial extent, potentially inspiring new generations of scientists, philosophers, and explorers to push the boundaries of human knowledge and capability. The economic implications of infinite versus finite space could affect investment in space technology, resource extraction, and long-term planning for human civilization's expansion beyond Earth. The question of whether space ends ultimately confronts us with the limits of human understanding and the boundaries between scientific knowledge and philosophical speculation, revealing both the power and limitations of rational inquiry into the nature of reality. Current scientific methods based on observation, experimentation, and mathematical modeling provide powerful tools for understanding the universe, but may ultimately be insufficient to resolve questions that involve truly infinite or transcendent properties of space and time. The very concepts of infinity, eternity, and absolute boundaries push against the limits of human cognition, which evolved to navigate finite, local environments and may not be adequately equipped to grasp the ultimate nature of cosmic structure. Mathematical frameworks provide abstract tools for reasoning about infinite and finite spaces, but the relationship between mathematical models and physical reality remains mysterious, raising questions about whether mathematical truths about infinite sets and geometric structures correspond to actual properties of the physical universe. The history of science reveals how human understanding has repeatedly expanded beyond initial limitations, discovering new phenomena, developing new theoretical frameworks, and finding ways to probe previously inaccessible realms of nature. Future developments in physics, mathematics, and observational technology may reveal entirely new approaches to understanding spatial extent that transcend current conceptual frameworks, similar to how quantum mechanics and relativity revolutionized classical physics. The interdisciplinary nature of questions about spatial boundaries requires collaboration between physicists, mathematicians, philosophers, and other scholars, demonstrating how the deepest questions about reality often require multiple perspectives and methodological approaches. The ongoing dialogue between theoretical predictions, observational evidence, and philosophical interpretation continues to refine our understanding while revealing new mysteries and questions that extend human inquiry into ever deeper levels of cosmic structure and meaning. Whether space ends or continues infinitely, the very process of asking this question and seeking answers reveals fundamental aspects of human nature, demonstrating our capacity for wonder, our drive to understand, and our ability to contemplate realities that far exceed the boundaries of everyday experience. When we ask the question, does space end? We are really confronting one of the deepest mysteries that human beings have ever dared to consider, a mystery that bridges physics, cosmology, philosophy, and even the limits of imagination itself. The very concept of the ending suggests boundaries, limits, edges where one thing stops and another begins. In our everyday experience, nearly everything we interact with has some kind of end. A road eventually reaches a junction. A book concludes with its final page. A human life ends with death. These endings are so central to our lived experiences that we almost instinctively assume that anything must have an end. And so when we look upward into the night sky and try to extend our imagination into the universe itself, we are tempted to ask where it stops, where the cosmic wall is, where the last star shines before a vast nothingness. Yet the notion of a space ending is far trickier than it first appears, because to end implies an external context. If a road ends, it ends into something else, like another road, or grass, or desert. If a book ends, it ends with silence or with the absence of pages. If space itself ended, what would lie beyond that boundary? Would it be a kind of absolute nothing, not even empty space, not even the absence of matter, but a non-existence that is impossible for the human mind to visualize? Or would the end of space be more like the surface of a sphere, where what appears finite to the being walking upon it is in fact unbounded, because moving in one direction long enough eventually brings you back to where you started? These kinds of questions make the problem so profound that every attempt to answer it spirals into more questions. The modern understanding of cosmology, driven largely by Einstein's theory of general relativity, tells us that space is not just a static container into which things are placed, but an active, dynamic fabric that is shaped by matter and energy. Galaxies, stars, and even light itself move along the curves of this fabric. And so when we ask whether space ends, we are not just asking about some box or cage, but about the very fabric that gives reality its shape and permits motion, distance, and time. In some cosmological models, the universe is indeed infinite, stretching without bound in every direction, such that asking about an edge is meaningless. If the universe is infinite, then space does not end, and there is no boundary beyond which there is nothing, because there is no beyond to speak of. Infinity, however, is not something our minds can easily grasp. We can say the words, but to actually picture an endless universe that has no limits is to engage in an exercise that stretches imagination to the breaking point. On the other hand, there are models where the universe is finite but unbounded, similar to the surface of Earth. The Earth is finite in size. You can measure its diameter, but it has no edge. You can travel forever without falling off. In this view, space might end in the sense of being finite, But it would not end with an edge or boundary. It would curve back upon itself, closing like a higher dimensional surface. But then again, other possibilities suggest that the universe could be finite and open, or even part of a larger multiverse, where what we call a space is just one bubble in an infinite froth of cosmic regions, each with its own space-time. If this is the case, then perhaps space does end, but only in the sense that our cosmic bubble has a limit beyond which lies something else entirely, maybe other forms of space-time, or maybe regions governed by different laws of physics, or maybe nothing at all that we could ever describe. And so the difficulty becomes clear. Every possible answer generates more mysteries. If space does not end, then we must contend with the unsettling idea of an infinite cosmos, something that has no boundary and no total size. If space does end, then we must explain what lies beyond that ending, which might be even harder to conceptualize. Our language and our intuition evolved to handle finite, tangible things in our immediate world, not to grapple with questions of infinity or absolute nothingness. So when we stretch them into the domain of cosmology, they wobble, break down, and leave us staring into an abyss of paradox. Science attempts to tame this mystery with mathematics, with observations of cosmic microwave background radiation, with models of expansion, with probes that extend further into interstellar space. Philosophy tries to grasp it with analogies, metaphors, and thought experiments. Spiritual traditions sometimes approach it by framing the cosmos as part of a larger mystery that cannot be captured by reason alone. Each perspective adds something, yet none give a definitive answer. This is what makes the question so powerful, so enduring. To ask whether space ends is to wrestle with the boundaries of knowledge itself, to press against the edge of what it means to know, and to recognize that perhaps there are domains where the human mind, magnificent though it is, can only ever grope in the dark, forever reaching without touching the final truth. Perfect raising hands. I'll continue with paragraphs 2 and 3, each 1,000 words, in the same continuous style. I'll keep going in sets like this until we reach 10, so nothing gets cut off. Whoa. When we attempt to probe the question more deeply, we are naturally led into the history of cosmological thought. Because the human mind has been asking a "does space end?" for thousands of years, though expressed in many different ways across cultures. The ancient Greeks, for instance, wrestled with the concept of infinity and the nature of the cosmos. Aristotle believed the universe was finite and bounded by a sphere of fixed stars, while others, like the atomists, imagined an infinite void extending without limit, sprinkled with countless worlds. Both positions reveal the tension between two equally difficult to grasp possibilities: a finite universe with some kind of limit or structure, or an infinite universe that stretches endlessly. Centuries later, medieval scholars working within theological frameworks often saw the cosmos as finite, enclosed, and ordered, reflecting divine creation. Yet even here, the problem arose of what existed outside the cosmic boundaries, a question that often left thinkers uneasy because it pressed against theological doctrines that placed God outside space and time. In the modern era, the Copernican revolution shattered the older idea of a neatly enclosed universe centered on Earth, opening instead the vision of vast space filled with stars, galaxies, and unimaginable distances. This shift did not answer whether space ends, but it expanded the scale so dramatically that the question took on new dimensions. By the time of Newton, space was conceived as an infinite, absolute stage upon which matter and motion unfolded. And in that vision, space clearly did not end. It was an infinite container, unbounded and eternal. But then came Einstein, who overturned that picture by showing that space is not an empty container, but a dynamic fabric intertwined with time, warped by gravity, stretched by expansion. With this new picture, the question, does space end, was no longer about whether the box has walls, but about the geometry of space-time itself. Is it open, closed, or flat? Does expansion go on forever, or will it reverse? Is the universe infinite in size or finite but unbounded? Observational cosmology has tried to address these questions using data from the cosmic microwave background, surveys of galaxies, and measurements of expansion rates. Current evidence suggests that on the largest scales, the universe is remarkably flat, which hints at either infinite extension or an incredibly large but finite size that appears flat to us locally. Yet even if cosmology leans toward infinity, we must admit the limits of our knowledge. We can only see out to the cosmic horizon, about 46 billion light years in every direction, beyond which light has not yet reached us. This visible universe may be just a patch of a much larger reality, perhaps infinite, perhaps not. And so, though science has advanced beyond ancient speculation, the essential mystery persists. We look into the night sky, we measure with telescopes and satellites, we refine equations, but still we are left with that haunting question. If space does not end, then we are adrift in an ocean without shores, an endless expanse in which every boundary we imagine is merely an illusion. If space does end, then beyond that ending lies something we cannot even conceptualize, not a place in the ordinary sense, but perhaps a condition beyond existence. Thus, history shows us that every age has struggled in its own language with this question, and though our scientific tools grow sharper, we may still be wrestling with the same paradox that haunted the Greeks and the medievals: how to think about endings and infinity in a universe that seems to elude both. In grappling with the possibility that space might end, one must confront the problem of edges and boundaries. What does it mean for space to end? In ordinary experience, endings are intuitive because they involve contrasts. The wall marks the end of the room. The shore marks the end of the sea. The skin marks the end of the body. Endings work because there is something on the other side of the boundary. But if space ends, what lies beyond that end? To imagine a nothing beyond is deeply confusing because even the thought of nothingness tends to smuggle in images of empty space, a black void, or silence, but these are still a somethings. Philosophers have long pointed out that humans cannot really imagine nothingness. We can only imagine the absence of familiar things within a background of space and time. So when we ask if space ends, the difficulty is that the very idea of an outsider requires space to exist there in some form, which undermines the question. Some thinkers have compared this to the experience of living on the surface of a sphere. From the perspective of a two-dimensional creature confined to the surface of Earth, the world would appear endless because one could walk in any direction forever without falling off. The surface is finite in area, but unbounded in experience. Our universe might be similar, not in two dimensions, but in three or more, where space curves back on itself in a way that produces finitude without edges. In that case, asking what lies beyond space would be as meaningless as asking a flat creature what lies beyond the surface of the sphere. Yet, even this analogy has limits because the sphere's surface does exist in a higher dimensional space. Do we then imagine our universe as existing within some higher dimensional arena, such as the theories of extra dimensions suggested by string theory or brain cosmology? If so, then perhaps our space does end in the sense of being a localized brainy within a greater multiverse, and what lies beyond is not nothing, but higher dimensional structures utterly unlike the familiar three dimensions. Others argue, however, that invoking such higher realms is unnecessary, that space itself may simply be all that exists, with no outside or beyond, in the same way that time has no before the Big Bang. The difficulty then is not just scientific but conceptual. Our minds evolved to navigate within bounded spaces, so the possibility of unboundedness or of absolute limits that cannot be crossed feels alien, unintuitive, and unsettling. Still, the pursuit of this question has led to remarkable breakthroughs in physics. Models of inflation, for example, suggest that the rapid expansion of the early universe may have created an infinite space, or that our observable patch is one bubble in a vast, frothy multiverse. Observations of cosmic microwave background anisotropies provide hints about the shape and curvature of space, nudging us toward the conclusion that it is flat and possibly infinite. But science is cautious, for we know only what lies within our horizon, and beyond that we cannot observe. Thus the question lingers unresolved, a ghostly presence at the edge of knowledge. When we ask if space ends, we are also asking about the limits of reason itself. Can human beings ever truly understand infinity? Can we ever truly imagine nothingness? Or are these concepts so foreign to the architecture of the mind that we will always circle them like moths around a flame, glimpsing but never grasping, asking questions that reveal more about the limits of thought than about the structure of the cosmos? In this way, the boundary of space becomes entangled with the boundary of human understanding, and to ask one is to confront the. Another way to frame the question of whether space ends is to consider the phenomenon of cosmic expansion, which has been one of the most important discoveries in modern astronomy. Edwin Hubble's observations in the 1920s revealed that distant galaxies are moving away from us, and the farther they are, the faster they recede. This suggested that the universe itself is expanding, that the fabric of space is stretching. If we run the expansion backward, we arrive at the Big Bang, a time roughly 13.8 billion years ago, when all of space was compressed into an unimaginably dense, hot state. But this raises another layer of the puzzle. If space began expanding from a hot, dense origin, does that imply that space itself had an edge, a starting boundary, or that it was expanding into something else? Many people instinctively picture the Big Bang as an explosion in pre-existing empty space, but cosmologists emphasize that this is misleading. The Big Bang was not an explosion in space, but the expansion of space itself. Every region of space was once closer together, and the fabric itself has stretched ever since. So in this view, the universe is not expanding into anything. Rather, the anything beyond does not exist because space is all that there is. Yet the idea of expansion tempts us to imagine an outside, a larger arena into which space grows. We picture a balloon inflating and assume there must be air around it. But in the cosmological analogy, the balloon's surface represents all of space, and there is no air beyond it. Still, the analogy can be extended. Just as the balloon's surface is finite but unbounded, the universe might also be finite yet unbounded, which means it could have no edges, despite not being infinite. But then, inflationary cosmology complicates this further by suggesting that the very early universe underwent a period of exponential expansion, producing a region so large that it may well be infinite. Worse still, inflation may never have ended globally, creating a multiverse of endless bubble universes, each expanding within its own dome. If that is the case, then perhaps our space does end, in the sense that our bubble has a boundary with others, but those boundaries are unreachable, forever receding faster than the speed of light, making them inaccessible even in principle. The physics here becomes dizzying as models suggest not only infinite expanses but also infinite variations, with different physical constants and different cosmic histories. In such scenarios, asking, does space end, becomes slippery because as space itself is redefined. Our observable space may have an end, the horizon of what we can detect, but the greater inflationary landscape may stretch endlessly, making any notion of end relative to perspective. Observationally, astronomers continue to probe for curvature, trying to see if space bends back on itself or stretches flat forever. So far, data suggests flatness, hinting at infinity, but with margins of error that keep open the possibility of finitude. Philosophically, this uncertainty forces us to dwell on the tension between the two great opposites, infinite and finite. Both are unsettling in their own way. An infinite universe challenges our sense of scale and uniqueness, suggesting that everything possible may occur somewhere. A finite universe challenges our sense of completeness, suggesting that there is some closure beyond which lies an impenetrable unknown. Expansion, then, does not resolve the question of endings, but amplifies it, showing us that the very dynamics of the cosmos are entangled with the mystery of whether there is a final edge or an endless horizon. The more we learn, the more the horizon of mystery itself expands, keeping the question alive, vibrant, and unsolved. The question of whether space ends also opens into the profound issue of time, because space and time are inseparable in the structure of relativity. To ask about the edge of space is also, in some sense, to ask about the edge of time. The Big Bang is often described as the beginning of time, which means that asking what happened before the Big Bang is a category error because time itself began there. Similarly, if space has an end, does that end coincide with an end of time? Imagine traveling toward the hypothetical boundary of the universe. What would happen? Would time itself grind to a halt at that edge? Or would you simply be unable to move beyond, trapped by the geometry of space-time that curves back upon itself? In Einstein's equations, space can be curved in different ways: positively curved like a sphere, negatively curved like a saddle, or flat. These curvatures determine not only the global shape of the universe but also its destiny. A positively curved universe might eventually recollapse, a negatively curved one might expand forever, and a flat one balances on the edge. Yet our actual observations suggest a flat geometry with accelerated expansion driven by something called dark energy, a mysterious component that constitutes about 70% of the cosmos. Dark energy complicates the question further because it implies that expansion is not slowing down but speeding up, pushing galaxies farther and farther apart until they become unreachable. If this acceleration continues indefinitely, then distant regions of space will forever recede beyond our observable horizon, leaving us in a kind of cosmic isolation. In this sense, the end of space for us might not be a physical edge, but an experiential one, where the universe we can interact with shrinks over cosmic time, even though the larger universe goes on. So, there is a strange relativity in the concept of endings. For us as observers, space ends at the horizon of what we can ever perceive, and that horizon grows more restrictive with time, even if globally space does not end. This realization highlights the role of perspective. An end for one observer may not be an end for another, just as the event horizon of a black hole marks a point of no return for those outside, but may not feel like a boundary to someone falling through. The entanglement of space and time also introduces quantum considerations. If space-time itself is emergent, as some theories suggest, then perhaps it arises from deeper quantum processes. In that case, the question, does space end, might be reframed entirely. Space could be like a phenomenon that emerges under certain conditions, with its end being the limits of those conditions. This line of thought pushes us toward theories of quantum gravity, holography, and the idea that space and time are not fundamental at all, but are approximate descriptions that break down at the smallest scales. In such a view, space may not end in the classical sense, but dissolve into something more primitive, a realm of information probabilities or abstract mathematical relations. Thus, the quest to understand whether space ends is not just about mapping geometry, but about discovering whether space-time itself is fundamental or derivative. And if it is derivative, then the end of space might not be a boundary in size, but a boundary in explanatory depth, a place where the very concept of space loses meaning. This realization is dizzying, but it shows that the question, rather than being naive, is in fact a doorway into some of the most advanced ideas in physics, linking cosmology, relativity, quantum theory, and philosophy in one profound inquiry. Another perspective that emerges when pondering whether space ends is the anthropological and psychological dimension of the question itself. Why are human beings so compelled to ask this? It may be that the notion of an end is tied to the way our minds structure reality. From childhood, we learn boundaries, the edge of a toy, the walls of a house, the limits of a playground. Our cognitive frameworks rely on demarcations to make sense of the world. Endings give us closure, and closure allows for understanding. So when confronted with something like the universe, which seems to resist boundaries and endings, our minds instinctively project those familiar categories outward, asking, where does it stop? Yet, in doing so, we may be committing a kind of category error, applying local intuitions to a domain that transcends them. The universe may not conform to the concept of the end at all, and yet our language forces us to frame the question that way. This tension reveals not just something about cosmology, but something about cognition. Humans are finite beings living in a finite environment, and so infinity is always something strange, external, and often frightening. The psychological discomfort of endlessness is well documented. Infinity can evoke vertigo, dread, or awe because it pulls us out of the safe confines of measure and proportion. On the other hand, absolute nothingness, the idea of a true end of space, is equally unsettling because it implies the absence of context, a state beyond being. In this sense, the question of whether space ends resonates not only in physics, but in existential experience. For some, the idea of infinite space evokes a sense of meaninglessness, because in an infinite backdrop, any particular location or event seems insignificant. For others, infinity inspires wonder, a sense of participating in something vast and sublime. Similarly, for some, the idea of a finite universe offers comfort, a contained order that mirrors human longing for boundaries. For others, finitude feels suffocating, as though we are trapped in a cosmic box. Thus, the question does not only describe physical reality, but reveals deep layers of human desire, fear, and imagination. And so, perhaps the persistence of the question across cultures and ages stems from the way it touches both the external and the internal. It probes the cosmos, but also probes the human condition. Whether space ends or not, the act of asking tells us something essential about the nature of consciousness, its yearning for closure, its struggle with infinity, and its endless drive to press against whatever boundaries it encounters. Scientific exploration also leads us to consider horizons, not just in the literal astronomical sense, but as conceptual markers of limits. In cosmology, one of the most profound discoveries is the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. This is about 46 billion light years, far beyond the 13.8 billion year age of the universe, because space itself has been expanding. Beyond this horizon lies a region forever invisible to us, not because it does not exist, but because its light will never have time to reach us, given the accelerating expansion of the universe. For us, then, this teaches us something important. The end of space may not be absolute but relative, defined by the observational limits of beings within space. A fish in the ocean cannot see beyond a certain distance, not because the ocean ends there, but because water obscures vision. Likewise, for us, the cosmic horizon functions as a kind of observational wall, a boundary of knowledge rather than of being. This idea has deep philosophical consequences. It reminds us that reality may extend beyond what we can ever know, and that our perception of the whole is always partial. It also resonates with Kant's insight that human knowledge is bounded by conditions of experience, and there may always be things in themselves beyond our cognitive reach. In this way, the cosmological horizon becomes a symbol for epistemological horizons in general. Moreover, the study of black holes reinforces this theme. A black hole has an event horizon beyond which no signal can escape. To an outside observer, the event horizon is a hard boundary, the end of accessible space. But for an infalling observer, crossing it may feel like nothing special. Space continues, though it leads to an inexorable singularity. Here, too, we see relativity of endings. What is an end from one perspective may not be an end from another. Extending this analogy to the universe, one might say that space could end in different ways depending on the frame of reference. For us, horizons define ends. But for the universe as a whole, such horizons may be internal structures, not true boundaries. Thus, asking whether space ends requires us to specify for whom and in what sense. The physical, experiential, and epistemic dimensions all intertwine, making the answer multifaceted. In a sense, then, the universe already does present us with ends, but these are ends of perception, not ends of existence. They remind us that while reality may be boundless, our grasp of it is always bounded. Another fertile avenue for exploring whether space ends is to turn to speculative theories that go beyond Einstein's relativity and standard cosmology. String theory, for example, proposes that the fundamental constituents of reality are not point particles but vibrating strings, and that these strings require additional spatial dimensions beyond the familiar three. Some versions of string theory suggest as many as 10 or 11 dimensions, most of which are compactified, curled up so tightly that they are imperceptible at macroscopic scales. In this framework, what we call a space is maybe just a slice of a higher dimensional structure. In the holographic principle, for instance, the information describing a volume of space can be encoded on a lower dimensional boundary, implying that our familiar three-dimensional space is not fundamental, but a projection of deeper informational structures. In many mythologies, the cosmos is finite and enclosed, often pictured as a dome above the earth, with waters or chaos beyond. The Hebrew Bible, for example, describes the firmament separating the waters above from the waters below, suggesting a structured, bounded cosmos. The mathematical concept of infinity itself presents fundamental challenges when applied to physical space, as it encompasses different types and orders of infinities that may have distinct implications for cosmic structure. Mathematicians distinguish between countable infinities, such as the infinite sequence of natural numbers, and uncountable infinities, such as the infinite set of real numbers between 0 and 1, with the latter representing a vastly larger type of infinity despite both being endless. When considering infinite space, we must grapple with whether spatial infinity would be countable, corresponding perhaps to discrete quantum units of space, or uncountable, corresponding to the continuum of real numbers that characterizes classical geometry. The mathematical framework of set theory reveals that there are actually infinite hierarchies of infinities, each larger than the previous, raising profound questions about which type of infinity might characterize physical space if it indeed extends without bound. Cantor's diagonal argument demonstrates that the set of all subsets of any infinite set is strictly larger than the original set, leading to an endless tower of increasingly large infinities that challenges our intuitive understanding of size and quantity. These mathematical insights suggest that even if space is infinite, there might be different ways for it to be infinite, with potentially observable consequences for the distribution of matter, the structure of physical laws, and the possibilities for conscious observation and interaction. The axiom of choice in set theory, which allows for the construction of mathematical objects that cannot be explicitly described or constructed, raises questions about whether physically infinite space could contain regions or structures that are in principle unknowable or unobservable, even with unlimited technological advancement. Gödel's incompleteness theorems demonstrate that any sufficiently complex mathematical system contains truths that cannot be proven within that system, suggesting that our understanding of infinite space might be fundamentally limited by the logical structure of mathematical reasoning itself. The application of non-standard analysis and hyperreal numbers to physics provides alternative mathematical frameworks for dealing with infinite and infinitesimal quantities, potentially offering new approaches to understanding spatial extent that avoid some of the paradoxes associated with classical treatments of infinity. Symmetry principles in physics impose powerful constraints on the possible structures and boundaries of space, revealing deep connections between the fundamental laws of nature and the geometric properties of space-time. The principle of translational symmetry suggests that the laws of physics should be identical at all points in space, implying that space has no preferred locations or natural boundaries that would distinguish certain regions from others. This symmetry principle, combined with rotational and boost symmetries, forms the foundation of special relativity and constrains the possible geometries that spacetime can adopt while remaining consistent with observed physical phenomena. The spontaneous breaking of these symmetries during phase transitions in the early universe could have created topological defects, such as cosmic strings, domain walls, or monopoles that might provide observable signatures of the global structure and extent of space. Gauge symmetries, which describe the redundancy in how we describe physical fields, suggest that many apparent properties of spacetime might be artifacts of our description rather than fundamental features of reality, complicating efforts to determine the true geometric structure and boundaries of space. The second law of thermodynamics states that entropy always increases in isolated systems, leading to the heat death scenario where the universe eventually reaches maximum entropy and uniform temperature, potentially affecting the meaningful structure and extent of space. However, the application of thermodynamics to infinite space presents paradoxes, as an infinite universe could maintain entropy gradients and energy flows indefinitely through statistical fluctuations, even after reaching apparent thermal equilibrium in finite regions. The concept of thermal time, proposed as a fundamental measure of temporal evolution in systems without external time references, suggests that the flow of time itself might depend on entropy gradients and energy flows, with implications for understanding how spatial expansion and evolution occur in different cosmic regions. Fluctuation theorems and non-equilibrium statistical mechanics demonstrate that systems can spontaneously decrease in entropy over finite time periods, suggesting that even in a universe approaching heat death, local regions of space could experience renewed organization and complexity through rare but inevitable statistical fluctuations. The vacuum metastability hypothesis suggests that the apparent vacuum of space might not represent the lowest possible energy state, implying that quantum tunneling could trigger phase transitions that fundamentally alter the nature of spacetime itself, potentially creating new regions of space with different physical properties and dimensional structures. Hawking radiation from black holes introduces additional thermodynamic considerations, as the eventual evaporation of all black holes would eliminate these cosmic entropy sources while potentially leaving behind remnants with exotic properties that could affect the global structure and evolution of space. The holographic principle's connection to thermodynamic entropy suggests the information content and thermal properties of any region of space are fundamentally limited by its boundary area, providing potential constraints on how spatial regions can grow, evolve, and interact over cosmic timescales. The emergence of complexity and self-organization in systems far from thermodynamic equilibrium demonstrates that entropy increase does not necessarily eliminate interesting structure and dynamics, suggesting that the future evolution of space might include phases of renewed complexity and organization even in the far future. Causal structure and the propagation of information through spacetime provide fundamental constraints on how different regions of space can be connected and coordinated, with implications for understanding whether space can have boundaries and how those boundaries might behave. The speed of light represents an absolute limit on how quickly information can travel through space, creating light cones that define which events can causally influence each other, and establishing fundamental limitations on the coordination and correlation of physical processes across large distances. The cosmic event horizon beyond which galaxies are receding faster than light due to cosmic expansion represents a boundary in spacetime, beyond which information can never reach us, creating effectively disconnected regions of space that cannot communicate or influence each other. These causal limitations suggest that even if space is infinite, it might be divided into causally disconnected regions that evolve independently, raising questions about whether such disconnected regions should be considered part of the same space or separate spatial domains. The topology of causal structure in spacetime can be quite complex, with possibilities for closed time-like curves, causal loops, and other exotic geometries that challenge simple notions of spatial connectivity and boundary conditions. The emergence of complexity and self-organization in cosmic structure provides insights into how space might develop internal organization and potentially boundaries through the gravitational aggregation of matter and the evolution of cosmic web structures. The cosmic web, consisting of filaments, sheets, and voids that organize matter on the largest scales, represents a complex hierarchical structure that emerges from initially small quantum fluctuations through gravitational instability and nonlinear evolution. This web-like structure suggests that space itself has developed internal organization and differentiation with regions of high and low density that affect the local geometry and dynamics of space-time. The fractal properties of cosmic structure, evident in the distribution of galaxies and galaxy clusters across multiple scales, indicate that space has developed self-similar organizational patterns that might provide clues about its global structure and potential boundaries. Percolation theory and network science provide mathematical frameworks for understanding how local connections and interactions can give rise to global connectivity and phase transitions in spatial structure, potentially relevant for understanding how boundaries or disconnected regions might emerge in cosmic evolution. The formation of supermassive black holes and their role in galaxy formation and evolution introduces highly nonlinear dynamics that can dramatically affect the local structure of space-time, potentially creating regions with exotic causal properties and modified spatial geometry. Active galactic nuclei and quasar activity demonstrate how energy and information can be distributed across vast regions of space through jets, outflows, and radiation, contributing to the organization and evolution of cosmic structure on scales much larger than individual galaxies. The interplay between dark matter and ordinary matter in structure formation creates complex feedback loops and non-equilibrium dynamics that drive continued evolution and organization in cosmic structure, suggesting that space itself continues to develop new patterns and relationships over cosmic time. Machine learning techniques applied to large-scale structure surveys reveal subtle correlations and patterns in cosmic organization that might provide new insights into the global properties and potential boundaries of space through statistical analysis of structural evolution. Quote, dimensional analysis and the physics of higher dimensional spaces provide alternative perspectives on spatial boundaries through the possibility that our familiar three-dimensional space might be embedded within higher dimensional structures with different geometric and topological properties. String theory requires additional spatial dimensions beyond the familiar three, typically 6 or 7 extra dimensions that are compactified on small scales, but could potentially affect the global structure and boundaries of the macroscopic dimensions we observe. The hierarchy problem in particle physics concerning why gravity is so much weaker than other fundamental forces might be explained by the dilution of gravitational effects through extra dimensions, suggesting that our understanding of spatial structure and extent might be fundamentally incomplete. All known Kaluza-Klein theories demonstrate how higher dimensional spacetime can give rise to apparently fundamental forces through the geometric properties of compactified dimensions, indicating that the forces governing cosmic expansion and structure formation might reflect the topology of hidden spatial dimensions. The possibility of large extra dimensions, accessible at relatively low energies, could provide new mechanisms for understanding dark energy, dark matter, and other mysterious cosmic phenomena through the interactions between ordinary matter and fields propagating in higher dimensional bulk space. Brainworld models suggest that our three-dimensional space might be a membrane or surface embedded within a higher dimensional space, with implications for understanding cosmic boundaries as potentially corresponding to the edges or topology of this membrane structure. The holographic principle's realization in specific string theory models demonstrates how higher dimensional gravitational physics can be exactly equivalent to lower dimensional field theories, suggesting that spatial dimensions themselves might be emergent properties rather than fundamental features of reality. Experimental searches for evidence of extra dimensions through precision tests of Newton's law of gravitation, particle accelerator experiments, and astronomical observations could potentially reveal new information about the true dimensionality and structure of space. The mathematics of higher dimensional geometry reveals rich possibilities for exotic topologies, non-trivial fundamental groups, and complex connectivity that could provide new frameworks for understanding how space might have boundaries or connections that are not apparent from three-dimensional perspective. Information theory and computational complexity provide powerful tools for understanding the fundamental limits on what can be computed, simulated, or predicted about spatial structure, with implications for whether questions about spatial boundaries are ultimately answerable through scientific investigation. The computational complexity of simulating universe evolution with different spatial topologies and boundary conditions reveals fundamental limits on our ability to test theoretical models against observational data, particularly for infinite or very large spatial domains. Kolmogorov complexity measures the shortest computer program needed to generate a particular pattern or structure, providing insights into whether the apparent complexity of cosmic structure could arise from simple rules and initial conditions or requires irreducible algorithmic complexity. The Church-Turing thesis suggests that all effectively computable functions can be computed by universal Turing machines, raising questions about whether the laws of physics themselves are computable and whether this computability constrains possible spatial structures and evolution scenarios. Quantum computation provides exponential speedups for certain classes of problems, potentially enabling the simulation and analysis of quantum space-time dynamics and quantum cosmological models that are intractable with classical computational methods. The physical Church-Turing thesis proposes that any physical system can be simulated by a universal quantum computer, but the validity of this thesis for strongly gravitational systems and space-time itself remains an open question with implications for understanding spatial boundaries and structure. And so, information theoretic measures of entropy, mutual information, and algorithmic information content provide quantitative tools for analyzing the organization and complexity of cosmic structure, potentially revealing signatures of spatial boundaries or infinite extent through statistical analysis of observational data. The it from bit hypothesis suggests that information is the fundamental constituent of reality, with space, time, and matter emerging from underlying information processing systems, radically reframing questions about spatial boundaries as questions about information structure and computational processes. Cellular automata and other discrete computational models demonstrate how complex spatial patterns and dynamics can emerge from simple local rules, providing analogies and potentially direct models for understanding how the continuous geometry of spacetime might arise from discrete information processing substrates. The anthropic principle and fine-tuning arguments provide another lens for understanding spatial boundaries through their implications for the probability and distribution of observers within cosmic structure and their relationship to the fundamental parameters that govern cosmic evolution. The weak anthropic principle states that observed values of physical constants must be compatible with the existence of observers, providing selection effects that could bias our understanding of spatial structure toward regions and configurations that support complex chemistry and biological evolution. The strong anthropic principle suggests that the universe must have properties that allow for the development of observers at some point in its evolution. potentially constraining the possible topologies and boundary conditions of space through requirements for star formation, planet formation, and biological evolution. The landscape of possible universes in string theory includes vast numbers of possible vacuum states with different physical constants and spatial properties, raising questions about whether our observed spatial structure represents a typical or atypical example from this ensemble of possibilities. Eternal inflation scenarios combined with anthropic selection could produce a multiverse where different regions of space have different effective dimensions, topologies, and physical laws, with observers concentrated in regions where these properties support complexity and consciousness. The measure problem in cosmology concerns how to assign probabilities to different observations and outcomes in infinite or very large universe models, affecting how anthropic arguments can be used to constrain spatial structure and extent. Statistical mechanical approaches to anthropic reasoning attempt to quantify the probability of observer emergence under different cosmic conditions, potentially providing objective measures for evaluating the plausibility of different spatial boundary scenarios. The doomsday argument and similar probabilistic arguments about the future of human civilization have implications for long-term cosmic evolution and the ultimate fate of observers in universes with different spatial properties and expansion scenario. Recent developments in astrobiology and the search for extraterrestrial intelligence provide observational constraints on the frequency and distribution of complex observers throughout cosmic structure, potentially informing anthropic arguments about spatial topology and the conditions necessary for observer emergence. Quantum field theory in curved spacetime provides the theoretical framework for understanding how quantum mechanical phenomena interact with gravitational fields and spacetime geometry, with direct implications for understanding the physics of spatial boundaries and extreme cosmic environments. The Unruh effect demonstrates that accelerated observers detect thermal radiation in what appears to be empty space to inertial observers, suggesting that the properties of vacuum states depend on the motion and reference frame of observers, with implications for understanding the nature of empty space and spatial boundaries. Hawking radiation shows that black holes emit thermal radiation and gradually evaporate, providing insights into how extreme gravitational fields affect the structure of spacetime and the information content of spatial regions. The Transplanckian problem concerns how quantum field theory behaves when applied to situations involving extremely high energies or small scales, such as the earliest moments of cosmic inflation or the vicinity of black hole horizons, where conventional field theory might break down and require modification. Particle creation in expanding spacetime demonstrates how the changing geometry of space can produce real particles from quantum vacuum fluctuations, providing mechanisms for understanding how spatial expansion affects the matter and energy content of the universe. The Casimir effect reveals how quantum vacuum fluctuations create measurable forces between macroscopic objects, demonstrating that empty space has physical properties and energy density that could affect cosmic evolution and spatial structure. Quantum field theory predicts that spacetime itself undergoes quantum fluctuations at the Planck scale, suggesting that the smooth geometry of classical general relativity is an approximation that breaks down at the smallest scales where quantum effects dominate. The renormalization of quantum field theories in curved spacetime requires careful treatment of divergences and regularization procedures that might affect predictions about cosmic evolution and the behavior of spatial boundaries. Recent developments in conformal field theory and the AD-CFT correspondence provide new tools for understanding quantum field theory in curved spacetime through dualities with gravitational theories, potentially revealing new insights into the quantum nature of spatial structure and boundaries. Dark matter represents approximately 85% of all matter in the universe, yet remains completely mysterious in its fundamental nature. with implications for understanding cosmic structure formation and potentially the global topology and extent of space. The gravitational effects of dark matter dominate the formation and evolution of cosmic structure, from the smallest dwarf galaxies to the largest cosmic web filaments, suggesting that understanding spatial structure requires understanding the distribution and dynamics of this invisible component. N-body simulations of dark matter structure formation reveal complex hierarchical patterns of aggregation and evolution that provide detailed predictions for the internal structure of dark matter, halos, and their relationship to visible matter components. The cuspy halo problem and other small-scale discrepancies between simulated dark matter distributions and observed galaxy properties suggest either that dark matter has more complex physics than simple cold collision, less particles, or that galaxy formation involves feedback processes that significantly modify dark matter distributions. Self-interacting dark matter models propose that dark matter particles can collide and scatter with each other, potentially solving small-scale structure problems while creating new phenomena such as dark matter cores, offset distributions, and galaxy cluster collisions, and complex thermal evolution in cosmic structure. Warm dark matter scenarios, where dark matter particles have significant thermal velocities, would suppress structure formation on small scales and could affect the overall statistical properties of cosmic structure in ways that might provide information about spatial topology and boundary conditions. The possibility that dark matter consists of primordial black holes would connect dark matter physics directly to gravitational phenomena and space-time structure, potentially creating regions of space with exotic causal properties and modified geometry. Action dark matter models suggest that dark matter might consist of extremely light particles that form macroscopic quantum states, potentially creating coherent field configurations that extend across vast regions of space and affect the global properties of space-time geometry. The direct detection of dark matter through underground experiments, space-based observatories, or particle accelerator production could revolutionize our understanding of fundamental physics and its relationship to cosmic structure and spatial properties. The role of magnetic fields and plasma physics in cosmic evolution provides another perspective on spatial organization and boundary formation through their effects on structure formation, energy transport, and the dynamics of ionized matter throughout cosmic history. Primordial magnetic fields generated during cosmic inflation or phase transitions in the early universe could have seeded the magnetic field structures observed in galaxies and galaxy clusters today, potentially affecting the efficiency of structure formation and the organization of cosmic web filaments. The magnetorotational instability and other plasma instabilities drive turbulence and energy dissipation in astrophysical systems, affecting how matter and energy are distributed throughout cosmic structure and potentially influencing the global topology and connectivity of space through their effects on structure formation processes. Cosmic ray propagation through galactic and intergalactic magnetic fields creates complex patterns of particle acceleration and energy transport that extend across vast regions of space, potentially providing mechanisms for correlating physical processes across distances much larger than light travel. Times would normally allow. The interaction between magnetic fields and cosmic expansion creates adiabatic compression and stretching effects that could concentrate magnetic energy in certain spatial regions while diluting it in others, potentially contributing to the organization and differentiation of cosmic structure. Magnetohydrodynamic waves and other plasma phenomena provide mechanisms for energy and momentum transport that could affect the dynamics of cosmic expansion and structure formation in ways that depend on the global topology and boundary conditions of space. The generation of magnetic fields through battery mechanisms, dynamo processes, and other plasma effects continues throughout cosmic evolution, suggesting that the magnetic properties of space are actively evolving and could provide observational signatures of spatial structure and topology. Recent observations of magnetic fields in galaxy clusters, cosmic web filaments, and other large-scale structures provide new constraints on cosmic evolution models and potentially new tools for probing the global organization and connectivity of space. The interaction between magnetic fields and gravitational lensing creates subtle but potentially detectable effects on the polarization of background light sources, providing new observational techniques for mapping magnetic field distributions and their relationship to spatial structure. The philosophical implications of spatial boundaries or infinite extent connect to fundamental questions about the nature of existence, meaning, and value that extend far beyond technical scientific considerations and touch on the deepest concerns of human experience and understanding. If space is truly infinite, then every possible arrangement of matter and energy occurs infinitely many times, potentially undermining notions of uniqueness, significance, and meaning that depend on the special character of particular events or configurations. The existence of infinite copies of every possible person, including infinite versions of each individual with slightly different life experiences and outcomes, raises profound questions about personal identity, moral responsibility, and the significance of individual choices and actions. Infinite space would contain regions where every possible story, artwork, scientific discovery, and cultural achievement has been independently created infinitely many times, challenging conventional notions of creativity, originality, and intellectual achievement. The problem of evil and suffering takes on new dimensions in infinite space, as infinite instances of every possible form of suffering would exist alongside infinite instances of every possible form of happiness and fulfillment, and potentially affecting theological and ethical frameworks for understanding the nature of existence. The heat-death scenario in infinite space might allow for the spontaneous emergence of complex, organized systems through statistical fluctuations over vast timescales, potentially enabling forms of consciousness and experience to persist indefinitely despite the approach to thermal equilibrium. Finite space with boundaries raises different philosophical questions about what might exist beyond those boundaries, and whether the concept of beyond has meaning in relation to the totality of spatial existence, potentially requiring new conceptual frameworks for understanding completeness and totality. The relationship between mathematical infinity and physical reality continues to challenge philosophers and scientists, as it remains unclear whether abstract mathematical concepts can be directly instantiated in physical systems, or whether they represent approximations and idealizations of finite but extremely large quantities. The implications of spatial structure for concepts of justice, meaning, and purpose suggest that resolving questions about cosmic boundaries might require integration of scientific, philosophical, and perhaps spiritual perspectives on the nature of existence and human significance within cosmic structure. In the end, the question of whether space ends is less about arriving at a definitive answer and more about recognizing the vastness of the mystery itself, a mystery that stretches beyond the reach of telescopes, equations, and imagination alike. Science offers us models. The universe may be infinite and unbounded, or it may be finite yet without edges, curving back on itself, or it may be just one bubble among countless others in an eternal multiverse. Philosophy reminds us that the very language of en day and a beyond may falter when applied to space, because these words presume contexts that do not exist outside the universe itself. Spiritual traditions remind us that however we picture the cosmos, its ultimate meaning may not lie in geometry or boundaries, but in the sense of wonder and awe it evokes within us. Psychologically, the question touches the deepest layers of the human mind, which longs for closure but trembles before infinity, which craves order but is unsettled by nothingness. Existentially, the way we imagine the universe, finite or infinite, shapes how we imagine ourselves, our lives, and our meaning. And yet, perhaps the greatest gift of the question is not an answer, but the invitation it extends. The invitation to wonder, to stretch thought to its limits, to dwell in awe at the fact that we can even ask such things. Whether space ends or not, what matters is that we fragile beings on a small planet can look up at the night sky and dare to ask what lies beyond. In that act of questioning, we touch something infinite, not in the structure of space, but in the capacity of consciousness. The universe may or may not have an edge, but our search for understanding has no edge. And in that endless seeking lies our deepest connection to the cosmos. So perhaps the truest answer to does space end? Is that the question itself never ends, echoing across cultures, sciences, and generations, reminding us that some mysteries are not to be solved, but to be lived with, cherished as signs of the boundless depth of reality and the boundless reach of the human spirit.